Okay, 7 o'clock. Let's get started. Today it's a review for the lecture 10, multiple representations. Uh, as the name implies, it's the same thing that but represented in different manners. All right, for this lecture, we have a game implementation and use of different data structure, and we open up the hook for you to see the implementation of a set. All right, you also see different representations of complex number. Of course, why we do that, here it's the rationale. As in many things in computer science, as you will see afterward also, there are some similarity, and we actually borrow a lot of the ideas in real life and use it in computer. The only thing advantage with computer is that it's very fast. All right. So, but in actual fact, what it does, it's more or less like what we deal with in real life. So we're going to see some examples. So for now, let me just say this it's what it is. All right, having multiple representation for the same thing, it's that because a thing, you see, like in a different kind of knives, I don't even know, I only know bread, meat, maybe. But you can see that they are all different. They are all cutting things, but what difference is that they can cut different kind of things in different efficiency. Okay, so we have different representation for different purposes. All right, even as we know that dishes, the vegetarian and non-vegetarian dish, but they are all the same name. But one could be its only make up with vegetable ingredients, while the other it's a meat. Okay, so why we have all this? It's then we have ways to use them differently. So you could use different representation at the same time. All right, that is if the system provide both to you. Okay. On the other hand, is that among all these representation, you pick one that is good for your purpose. All right. So how do we know it's for which is good? And we talk a little bit about that, and afterward we will see a little bit more, a few statements about it. All right. So efficiency is what we usually look for. Even nowadays with AI, you are training, you also want to do things fast. You want to train very fast and so on. And in actual fact, these days, the storage is really cheap as relative to maybe 10, 20 years ago. The CPU now it's more expensive, and the storage is actually cheap. But on the other hand, if it's not that it's cheap, then you use it. It has prompt. The prompts are as follow. All right, it's redundancies of representation, meaning that you have more than one representations in your system. Then you would have to maintain consistency. All right, because multiple copies, multiple representations of same thing, you have to be sure that both or all of them are representing the same thing. All right, just in real life, you have encountered this. We have for sure. My generation, we have. All right. For example, we take down our password on paper at home and on paper in the office. And the moment that you are asked to change password, you hate it, man, because you have to change the copy that you wrote down in the office and the copy you have it in at home. All right. And so at some point in time, during the transit between the office and the home, there's an inconsistency of the thing. All right. Of course, this inconsistency in this case, it doesn't really matter. For example, another case here that I put down is that we all have web pages. I have my one web pages you can see under SOC, and you may have your own also. Nowadays, this world is such that all our web pages are cached somewhere and some other nodes in the World Wide Web. And those copies are not necessarily up to date because they could be a cache of a day ago or even maybe a week ago. and you may have changed your own web page on the day to day, and you don't expect that this is propagated to all the nodes in the World Wide Web. All right, but this kind of inconsistency is temporarily, and it is not involving critical data, so there's no harm. Nobody care you added another line in your CV or whatever. All right, it's incorrect for those guys in America who see your CV 1 month ago. It's okay, right? But this can be a problem if you are talking about financial data, right? For example, bank records, it has to be consistent all the time, in a way that the system has to have a single truth with respect to whatever is recorded. Whatever money you have in the bank has to be the truth and only one truth. So in such kind of cases, the multiple copies can pose problem. But on the other hand, you can have mechanism to actually lock your records in the multiple copies, as you will learn in distributed systems. And then you have to update all the copies before you can release the lock. All right. So indeed, there's no free lunch, but there are also mechanisms or solutions or protocol to resolve it. All right. And then to the user, the issue is then which representation to use. All right. Uh, so does it need to know? Actually, also that is the other question, right? Does it need to know in the case of our complex number, right? Actually, complex number is also a primitive data type in Python, but in our lecture we actually created it for you. Right, in a complex number, do you really need to know its Cartesian coordinate or is it polar coordinate? All right, so hopefully, actually, the user need not have to know about it. All right, and this is in the spirit of computer science, where we always develop things layer by layer. So the user of a complex number will only stay on that using of the complex number without knowing the actual implementation of the complex number. And I actually mentioned that in the case of rune, right? The picture language. You don't have to know how the runes are generated. You just call it, and even if the implementation of the rune is changed, you may not notice it actually. So it is just meant for efficiency, that somebody changed the ball, but of course that somebody who is working on that layer has to have ways to test and make sure that whoever is going to use it on a higher level will not hit problem as a result of the change. Okay, and that the point about how do you know which is the representation to use, if you should you want to know it, or for the system programmer. When we say system programmer, means that the guy who we divide into system programmer and application programmer. System programmer are those people who deal with the system matter, right? In this case, whoever presented to you the rune picture language, the one that who developed the picture language, that person is in the system level. All right, so this system level person will have to maybe study the past history of how things are being used by the application layer, application people. And then we'll take some statistics and so on, all right, and see which is the better the representative to use. Should he or he has to change the representation or not? All right, so these are things that resulted from having possibility of creating multiple representations. All right. Right, and there are also mathematical analysis. If you cannot collect real data, all right, and here in the past history, maybe there are some mathematics analysis that you can use to understand which is a better representation. All right, to start with, all right, along the way, you can still swap or change the representation. So multiple representation could be there at the beginning, but it may evolve, and one of them being removed without the application people knowing about it. As long as you don't infringe getting into the too deep the layer, you are staying on that layer without touching anything below. you will be safe. All right, because computer is developed in a layer by layer manner. Okay, and you can also kind of like relate to it that nowadays the AI is trying to do what the human are doing, and the computer are trying to mimic that. In actual fact, this is also what I started off this discussion, that there are multiple representation. But still there are things which are actually mimicking, similar to what we have in real life, with the exception that computer is so fast that each operation takes 10 to the power minus 12 or whatever, the kind of time step that the computer is doing. So you thought that computer is more superior, but in fact it is not. It is just doing step by step. Of course, the pair processing doesn't mean that it is even more powerful. It's just that it can do things concurrently, all right, and also very fast, right? And AI, as it's trying to do, is to again mimic the intelligence of the human. So it is, in a way, even more copying what a human can do, right, in the computer. So I would like you to have this in mind, in some sense, for your study of the computer science. In a sense that once you can see the similarity, and there's a possibility that they will be able to impress upon you much longer, and you will be able to learn in a more enjoyable manner in some way. Okay, so I'm going to present to you two examples. Example one section about amortize, and example two about move to the front. Okay, actually I have example three, but I have taken that out because I want to reserve that for next week. I can mention that, and then you can guess what it is, actually, if you want to post it in the forum. I started the forum posting early today so that get you a little bit heads up to see what I'm talking about, and you can start thinking about it. Okay, so part B is to start with some of this stuff that implemented in computer. Actually, it mimic what it's in the real life, and in fact, it has very often support of mathematics. Of course, you have to discover this mathematics yourself or ourselves as a human to be able to then explain some of this stuff are good. Okay, here is a leading kind of the story into the amortized analysis. So this is what I wanted to check with the word amortized comes from. Okay, suppose you have a class of 40 students, all right, to take turn to clean up the classroom every day. Okay, what we can do is that everybody does the work. All right, everybody contribute. Okay, so there are two possibilities. The first one is that the whole class does it every day. Then in this case, because there are more people, you may just need 15 minutes. But actually, this 15 minutes, it's kind of like uh, a lot of time, because why? Because when you have more people, of course, there will be more communications, and communication, it's part and parcel of the cost, right? You will delay things a little bit. On the other hand, you can actually make it into 20 groups, 20 pairs of students for the 40 students, and make them into 20 pairs. And in each month, we have 20 working days, roughly, usually between 20 to 22 days in a month, working days. All right, so if you only have one pair of students to do it each day, all right, but there are 20 pairs, so everyone is allocated to one day in a month, okay? So in one day in a month, but then because there are only two persons, so you may need to take 1 hour, 60 minutes to do it. Well, the question is, which is better? Okay. First case is clear that for 20 days in a month, everybody does it. So everybody need to spend 300 minutes. All right. I hope I didn't make any mistakes. All right. So which is equal to 5 hours. All right. So basically, each of the student is spending 5 hours a month to clean up the classroom. On the other hand, in the second case where each one is only spending 1 hour in a month. All right. So basically, each pair of student is shake leg until his turn or their turn on that month, then they do. All right. So most of the time they are free, and once in a while, in a month, once, exactly once, they are busy. Okay. So in the first case, it would be something like it can be the worst case or I mean that this worst case with respect to algorithm. It's that, for example, the sorting. The worst case for the bubble sort, maybe it's not bubble sort. The worst case for quick sort that you saw is to take a guy which trying to divide into two parts, but it never get divided, and as a result, the worst case is n squared. Okay. On the other hand, the good case for the maybe the bubble sort, the improved version of the bubble sort, is that when the whole set of input is sorted, and in this case, you only need to spend O(n) time, and where n is the length of the input to finish out the job. All right. So this is worst case can be O(n) squared. Same for bubble sort. Worst case can be O(n) squared. But good case, in the improved manner, it can be O(n) only, linear versus n squared. All right, average case usually talk about as in a random input. So what you do is that you take all kind of inputs, or maybe all kinds of input, and the probability of each of these input, in this case, will be the n factorial divided by a 1 over n factorial. All right, that will be the probability for a random number. And that will be the average case that you have to spend. So you sum out and then you divide and then you pay this average case. Now, here is the one that is most interesting, amortized case. There is no assumption on the input pattern. Basically, you give me any way of doing things, all right? Any pattern, as you will see in the next example here. I'm going to give you the measurement in the sense of I will take all the total cost divided by the number of operations. All right, then that will be my cost. That means that I will average out whatever input that you give me. I don't care. All right, there's no assumption on the input, and I'm going to get you a number. So in this case, all right. So in this case, if you talk about this, students. So if you talk about it, so each one is it's spending 1 hour, right? Each student. So you have 40 students. So there are 20 days. 20 days, you only work on 1 day or 1 hour. So for each student, actually you only less than 5 minutes. 60 divided by 20 is only 3 minutes. All right. So the cost to each student is 3 minutes per day. All right. So instead of 15 minutes when they are all working at the same time. All right. So the amortized cost is 3 minutes as compared to 15 minutes. Actually, it's quite good. All right. So let me give you a more computer science example here. This is a real thing. I'm talking all the time. So if you want to interrupt me, go ahead. Otherwise, I will just keep talking. This is it's just a kind of a philosophical, and it helps with learning. All right, so this is called the memory management. Okay, this is really happening, right? In the memory management systems, okay, when you ask for an array, okay, or in this case, a list, okay, in Python, it's called a list. The system doesn't give you a whole, you know that you can add a lot of things to the list, endless basically. Okay, but you don't expect the system give you the endless storage in one go. You should know that you should believe that the system actually give you some number, and then at some point, if you need to, it will give you some more. Okay, so that is what is happening. So the system give you, for example, 16 slots only. All right, as a beginning. All right, it doesn't give you the whole world to work with, because the array that you needed could be just one of the many arrays that you needed, and there are many other arrays that you need to satisfy also. So I don't expect that you get all the memory available in the system to be given to you. Okay, so what happened then when you use up all the 16 slot by adding 16 items into it already? All right. So in this case, one smart way to do things is doubling. Okay, and this happened very common in computer science. From 16, I double it to 32 for you. Okay, I will make you 32 slot now. Okay, and of course, this 32 slot, it could be an extension of the original 16 slot. And in this case, you don't have to do anything, just use the number 17, number 18, and so on to put in new items there. But it's also possible that these 16 slots that given to you, the following memory space is no longer available. Okay, you have to copy the 16 slot out to the 32 slots that are newly allocated to you. All right. So you see that the moment that you hit number 17 items, the system, you got no choice. You have to pay the price of copying the 16 slots to the new location. Okay. But as you will see shortly in here, that this doesn't hurt you actually. In the long run, in an amortized sense, you are not paying a lot. Okay. Then it repeat the story. If you have now you have if you have 32 slots use up, then what happened? The system will give you 64 slots. All right, and the 64 slot use up, then it will give you 128 slot. All right. Each time you double it and then spend effort to copy it too. All right, you need to copy. Well, we assume you copy it. Okay, if you don't copy, then you're happy. All right, but you do have to copy sometime if the memory are not contiguous given to you. So the question is how costly this approach is. All right, so what you are seeing here is that you are happy, for example, from 16 to 32, you're not happy on the 17 item, but after the 17 item, all the way until 18, 19, all the way until 32 items, you are just simply appending it because the memory space is there for you. Okay, so there's you don't hurt, you don't feel any hurt. All right. So you can sense that it's not so expensive, and you are pretty much happy, very happy often, like the pair, you have you only have work only one day, once in a while, once in a moon, in a month, a blue moon. Okay, well, it's once in a month. Okay. All right, so you are happy most of the time, except that when you need to copy out things. All right, here's the calculation. Actually, there's calculation. So the calculation goes this way. This is a calculation. It's called, technically, this is the calculation you can apply. Okay, so the claim is that each append costs you 3 units. So what it means is that the amortized cost is O of 3, which is O of 1. So you're paying instead of 1 unit cost to each append, you're actually paying 3 units. How does this 3 unit being used? All right. So for example, starting with having 16 item, now you're on the 17 item. Okay. What happened is that we pay 3 units. All right. We pay this 3 unit. The 17 item actually pay 1 unit on the actual append. All right. That means that he himself consume it. He keep 1, and then he give 1 to the first item, right? Because he has 3 units, right? So at this moment in time, 17 item actually has a credit of 1 unit. The first item also has a credit of 1 unit. Then when the number 18 items come along, he also pay 3 units. He use up 1, all right, for the actual copying, actual append. Then he keep 1 as a credit for himself, and then he give 1 to the second item, all right, and so on. So when you hit the number 32 items, you can imagine everyone has a unit on hand. Okay. And everyone has basically a credit on hand, and then that guy can use it to copy into an array of 62 items. All right. and you repeat this. So the moment that you need to pay for copying to a bigger array, you have a credit already given to you. And that credit was given by someone else that pay for it. And all in all, you do have a credit all the time that you needed to copy. So therefore, every copy just need a charge of 3 units. And this 3 units is good enough to pay for yourself on a pen, keep one for yourself, and give one to the earlier guy. And as a result, all in all, you only need to uh, when time comes to do the copying, you are actually paying O of 3 only. And in fact, it's O of 1. So this O of 1 is the cost per a pen. All right. And so you can imagine, so even though I don't give you the whole world, but I'm also not penalizing you because you are actually doing the pen only in constant time each time. All right. So you okay? At this moment, it's good to take a pause. You okay? Give me a check. All right. There are many of these things actually in computer science. The one of these very difficult one is union find. This particular analysis is very straightforward. Okay, because of the idea of doubling. All right, but this one union find you can find for yourself. This is a huge. It take a few pages to talk about it. I can't even remember. It got to do with Ackermann function that how you do union find. I mentioned this data structure before. All right. So you're okay. Then let me move on to the second example. This second example, is similar to what you have at home, right? Suppose you have a bookshelf. How do you actually arrange your books or notes on the shelf? All right. Of course, you can also imagine that you do hashing, right? You know that hashing in the sense of you use the title to hash or you use the author to hash or whatever. All right, in computer that's the same thing. But here, actually, it's a simple one. So what is this simple one that well I have in mind here? It's basically in a linear order. So you are giving you have your notes in a linear order. Of course, your notes is there not just by me, right? It's not just there for show only, but you want to refer to it. So, for example, you have a list, or instead of notes, we talk about number. You have a list of a number 10, a number 20, a number 11, a number 22, and number 15, and number 18. All right. So the strategy is like this is one, this is a mathematics note, this is physics note, this is chemistry note, this is computer science note, or this is history, geography, whatever. All right. So now you want to look for computer science. So you look one. The only thing different from computer with us human is that computer got no choice. It has to look one item at a time. So you check this guy. You check this is not what I want. This is not what I want. Oh, 22 is what I want. Okay, so 22, he found it. So once he found it, what did he do? Of course, you can take it out and read it and then you put it back, right? But the strategy here is to tell you that instead of doing that, you you move 22 with 11, you swap the two place, so it become 22, 11 instead of 11, 22. And then you do some more. You swap 22 with 20, so 22, 20. Then you swap 22 with 10. All right. So at the end, 22 move to the front, the rest move to the back. That is what this is. This is called move to the front strategy. What the rationale for this is that if you take computer science note out, all right, this moment, you may want to, there's a high chance that you may also refer to it again in the near future. Okay, so you move it to the front. All right, this happens in compiler. If you know what compiler is when you write a program like Java, you need to go through a compilation to make it into machine code. In compilation, there are many steps. One of the steps is to make sure that you can find the variable names in somewhere. Okay, so you need to search one by one and so on. All right. So, and if you have found that variable name, maybe in the near future, you're going to use that variable name again. You will need to check on that guy again. All right. So, this is what is called a move to the front strategy. It happens in computer science. All right. And, you can relate it to your real life. Like you take this computer science note, you read it, you want to keep it in the front. All right. So the same thing, here, right? First search for 22, which we did. Then next, maybe we search for 22. All right. Then if 22 already in front, then nothing, you don't have to do anything. The next is that you search for 11. All right. In this case, 11, not this one, not this one, not this one, this one. 11 is here. So you have to move 11 all the way to the front and the rest push to the back. So it become 11, 22, 10, 20, 15, and 18, which is this. Okay. All right, when you search for 15, then you will become something like 15, 11, and then 22, 10, 20, and 18. All right, you know what I mean. All right, if you search for 15 again, you will get the same thing. If you search for 18, now it become 18, and then the rest. The rest. 18 go to the front, and the rest go to the back. All right, now I argue that I claim that actually you are uh, actually you're doing very good in this case. So this is can be proven. So the proof is in here. It takes a while to understand this. All right. So the proof says that basically this approach is no worse than the superhuman being. All right. In this case, we can call it a god. All right. The god is able to do, if the god knows about what you're going to do. First, I'm going to search for 22. Then I search for 22. And I search for 11. I search for 15 and so on. If this thing is presented to the superhuman, all right, and then that superhuman should be able to arrange this guy somehow, right, to suit this searching pattern. This is called the offline. Okay, this is the offline approach. Basically, this superhuman is actually told about all these operations. All right. So this superhuman supposed to be able to do very well, the best, basically. All right. But this superhuman must still pay the price. If this is the list originally given, if the superhuman actually rearrange it in this manner, like what we do, he also pay, in this case, pay how much? 1, 2, 3. You have to pay 3 units to move this guy to the front, and you also have to pay 1, 2, 3, 4 units to identify 22. This part is no different between the superhuman and we, the human, okay? But the claim is that this superhuman is doing this offline, meaning that he has foresight, he can see all these beforehand, and then he has the the luxury to be able to rearrange this thing first to suit his searching. All right. And if he can do that versus us, we are online. We only do things one at a time. We do not know after searching 15 what is coming after that. So we are online. So we are online to search for 15. The next thing we do not know. We will only do the same as moving things to the front all the time. All right. So we are online while the superhuman is doing it offline. Okay. In allowing this superhuman versus us, the claim is that this superhuman, we are not going to be 4 times worse than the superhuman. What is this 4 times means? This 4 times means is a constant difference to the superhuman. All right. So we are very good. All right. So and some of course this number is overestimate. Okay, and in fact, in the real thing, it can be much smaller than this. All right, so the superhuman, it's not going to be super to extreme, become unbearable for human to meet. Okay, so this is why, of course, the math is in here. That if you are interested, you can see it. It's not so difficult still, but it still needs some attention to be able get through this. All right. So let me just unblock. All right. So we are talking about here. It's let me just recap. It's that we are looking for the key. In this case, this key is refer to computer science. All right. So it has an associated information. All right. As usual, there's always associated information for each guy that we are looking for. All right. So this is called move to the front approach. Okay, and I say that you are going to find a particular item in the list and go through the list to find it. You got no choice but to pay one cost. You pay one search, one. Now there is no binary search here. It's only a linear search here. Once you found it, you move it to the front to be ready for the subsequent search. Right? This turned out to be very powerful approach, efficient as compared to the superhuman approach. Okay. And in this case, the superhuman knows the entire access sequence, meaning that he knows that search what is coming after each search. That superhuman is presented with all the searches, all right? And then we talk about how much cost he is paying if he knows how to arrange things. All right, he knows that if we're going to be nasty, for example, in this example, 18, you would, because 18 is coming up, right? While he moving 15, he may also move 18 in front, right? Together with the 15 and so on, to preempt some of these bad cases that one can design to fool us, not to fool him. Okay, us because we are online, we don't know what is coming up, but this superhuman knows what is coming up, so he can rearrange things to it. But still, ultimately, he cannot be more than 4 times better than us. Okay, so we are only paying a constant cost to what the superhuman needed to pay. Okay, so there is another example that I skipped for today. Actually, this got to do with OOP. All right, you will think about OOP. You can imagine the object-oriented programming, the way the mechanism how object-oriented programming, which is in our lecture, if not 12, will be 13. All right, so you take a look at that, and the object-oriented programming, the mechanism that how object-oriented programming come about, it's very much like what we are communicating in real life. Okay, so let me just conclude this in an early ending. All right, the summary are all these interesting points that you may have encountered most of them already. First of all, you should pause when you see something. It's not that we computer science are very sophisticated at time. Some of these ideas that you see are pretty straightforward, and they all come from real life. And in fact, once you can exercise these techniques from real life to computer science, the only thing missing is that you have to use mathematics to explain what you do. And luckily, as many of the interesting prompts that we have, that we use our real life to address them in computer, they do have some of these mathematics to support our way of doing things. This is kind of interesting. Yeah, all these analogies in what we do in computer science with the real life. Again, I cannot say this more again that the computer is just simply running faster than us in the speed, but our brain is also very fast in processing things. So it took us to reach the AI stage these days. And still AI has hallucination. It cannot still do all the things that human can do. All right, of course, they can remember things very well because it's all hard-coded into some storage that they can access it very fast. Whereas human, if you have 1 year ago conversation, we already cannot recall most of this unless you have a photographic memory, which most of us are not. Maybe a very little percentage of the people are in that talent. Okay, and next point I wanted to say is that again and again, the course is divided into algorithm in the front and then data structure in the back, and then a combination of data structures with algorithm into paradigms. Okay, so maybe I can say that first half algorithm, second half data structure, and then finally combine into paradigm. Okay, algorithmic paradigms, right? Basically, you have standard way of doing things with standard data structures that you must have. The third point that you saw just now was layer by layer, all right? The different representation. If you stay within your layer, anyone does anything to the lower layer is not going to affect you. You are still safe. So this is always, we always have this thing, they call it API, application programming interface, right? You always do the the thing that you are told you can, how you can talk to the lower layer through API. All right, basically those standard function that provided to you. Application programming interface. All right, the fourth point here is that it's halving and doubling. So you saw doubling here, okay? Halving is just the converse, and it happens. So all this halving, like in the planet, in the merge sort, you saw the halving of things, and then in the here you saw the doubling. So all these things are common in computer science. Of course, you can vary to one third, two third, and so on, and you can also achieve some of the interesting stuff. But ultimately, this halving and doubling, it has reached the logarithmic complexity. It allows us to reach in this case here it's constant, but usually it halving and so on, it give us the logarithmic log for our time and space complexity. All right, and we talk a lot about managing complexity actually. So, and this is how within we divide and conquer, and so it's also divide. It's also a kind of halving, and this is the strategy that you have. I believe among all these things, you will see it coming up in your midterm. Yeah, that's all I have for today. Any question? At 8 o'clock, I'm going to do the recitation number 5. That will be the recitation that you needed to study for your midterm. Any question? You can ask me anything about the midterm. The first page of the midterm is already published, and your sitting arrangement is also published. You okay? Give me a check, and then we can take a short break, 15 minutes. Okay. All right. Even though I talk a lot, mainly in words, but actually, you also saw, in some sense, some calculations, and the math is there to actually smooth things out. Let me try to call this guy, see how complex this is. I studied this before. It's only 2 pages, maybe. Yeah, 2 pages. So if you're interested, you can study. Just it's very dense. It's always proof, as I told you last week or the week before, that it's always condensed in statements that one follow another, and yet it covers all the possibilities that you can think of. All right. Hmm. Okay. If you have no question, let me see any question. Let me just sorry, submit them. Okay, here's the seating arrangement. All right, they are all at the School of Computing, Com1 building. That's the main building, level 2. All right. Your name should be posted outside. The SR1 is here. This is the biggest room. And then SR3 is here. And then VC room is here. Okay. And the page 1 of the paper is this one. There are 3 questions only, but question 1 has many parts. And so these are usually short answer. And question 2 and question 3. Actually, they are all kind of like short questions because you don't have to write a lot. Yeah, you don't write a lot. Yes. Okay. If no, let's take a break. Oh, yeah, there's something asking. What are the units and credit for? Oh, okay. Why we search 22 and 15 twice in the search example? Okay, okay. These are just examples. It can be anything. It can be in this case maybe you search for 10. Then you will have to change your array, become, what is this, 10. In this case, the 10 will have to come to the front and you will have 10, 15, 11, 22, 20, 18. All right, then this one will be 10 here. This 10 is gone from here. So you will get this. All right, these are just example. The midterm is written, right? Yes, the midterm is on paper. Okay. Are there any method marks for the midterm or practical? Uh, okay, for question 1, usually no, because these are all short answer. Either you will get it or you don't get it. Of course, we will see whatever we mark, you'll be returned to you and you can contest. Okay. So you can take it that there's no method marks. But in sometimes if you just careless in your typo or something, you can contest and we may give it to you. Is there any tips for the exam? The tips is in page 1. No more tips. Oh, if you study, you have been following my review and my recitation and the TA's tutorials, you should be okay. Of course, there are certain depth to what we trying to catch you, in a sense that it can be sometimes tricky. So be careful, right? Okay, there was a first question. What are the units and credit for a pen and amortization cost? This is always the way that amortization is analyzed. All right, amortization analyzed by paying upfront, by giving credit first, and then collect back the credits, as if that I give you some money first, and then you can use that money to pay for something else. This is a kind of a way that amortization can be argued, and it happens for union fine also. If you take a look at the union fine if you want to. All right, that's all I can tell you. Oh yeah, of course. For midterm, you're not supposed to have any. You will look carefully. You're not supposed to have any electronic devices with you. Okay, the use of mobile phone, laptop, and calculator is not allowed during the test. If found using any of these equipments any moment from now till your scripts have been collected, you will be given a 0 mark. If our contest fail, what do you mean contest? I don't understand. So
Uh,
Rui Yang.
Hello. Yeah, it's
Yeah.
like contesting of marks. Let's say after you get the scripts back.
Oh, 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 yeah, maybe because it's both way. Just like you appeal in a court, right? Your appeal may get through, you get less, you get some credit. Your appeal may fail, and then we see that we may have to penalize you. Yes, you may get penalty if you appeal, but we try not to do that, huh? We just reserve the right. Okay, that's all. Oh, oh yeah. How do you start to analyze this kind of function time complexity? Oh, uh, or it's just like what should I be thinking about? Why you should think about like you can usually you try n equal to let's say 5 and then you trace it out and get some sense about it and then you generalize it to how it should be. Okay, I cannot I sort of the question is besides AP and GP, what other math concept needed to know for the paper? Generally, GP and AP it's a must, and any other concept you need to. I hope not. Of course, the L'Hopital's rule, those kind of math, so calculus things, will not be there for sure. As to a little bit of maybe common sense of how you should count things, maybe those are the stuff. Uh, I will check my paper again, just to be sure. I don't think you need any more than AP and GP. Okay, but there's one thing that you should know for sure. It's in the last in years in so in okay, maybe that will be applicable for the final exam when we talk about matrices. You should know because it's covered in our recitation and tutorials. So those math where they appear in our math in your tutorial or recitation, we will assume you have to know. All right. Other than that, you shouldn't be penalized for not knowing some of the math. Okay. If should there be such a case, you can contest also. Right. But I remember one case, which I find more ridiculous last year or the year before. Somebody said that he cannot do A to Z, A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, Q, R, S, T, U, V, W, X, Y, Z. You cannot say you do not know that. The student asked for it during the test. I was a little bit annoyed, but I actually gave it to him by listing out A to Z, the 26 alphabets. The test topic are until chapter 8. Uh, Let me see. It's stated here. Lecture 1 to lecture 8, yes. All right, and concept on sequences. Sequences include list, tuples, dictionary, and so on. Okay. Even though recitation up to 5 doesn't have all those stuff, but it's lecture 8. Or you can bring your own draft paper. Do you have any general tips for analyzing time and space complexity? Okay, this is nothing more than breaking it down into something which you can digest. For example, just now you give the full, right? The full, it looks complicated, right? But you try to put in some n equal to 5 or 6 or 7. Then you can trace through and see what you understand about it. And then from there, you generalize it, and yeah, that makes sense. Okay, it's always trying small things to understand the big thing. And that is the concept about the syntactic versus semantic, right? We talk about that. Syntax versus semantic. All right, we talk about that. Hey, rough paper. No, 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 no. You can bring whatever paper you want. We give you in 8 pages. You can use the back of the page as rough paper. No extra paper you have to write. You're writing on the script. Okay? Ray Yang.
Yeah, yes, sir. Yes, prof.
Okay. Okay. You don't need rough paper. Yeah, you can bring your whole notebooks. You can bring your whole libraries. But I believe that your library will not be useful. You won't have time to check. You only need to summarize things, make sure that you understand a summary. Okay. I shall not answer anymore, and I can answer afterward at 8 o'clock. Okay. But for now, let's take 5 minutes break. Okay. Can you hear me? Okay. All right. It's 8 o'clock. We start. All right. Today it's recitation number 5. All right. Before that, just now there were so many questions about the midterm. Let me just anyone just come in after the review. If not, then I will basically just to quickly sum up, maybe. Let me get the chat. All right. This is an open book exam. Books are generally not useful. All right, as questions are designed as such. There's all this FAQ here. You can try. Should be here. All right, some of these questions. And you're not supposed to use any calculator, any laptop or whatever. All right, it's a written exam. You can bring your notebook, but not electronic version. Okay. Oh, there's a question of a telescoping series and other similar math concept. It is needed to know. Um, I believe I show the telescoping series in the recitation. If it is so, um, I would think this is it's a kind of tricks. So it's even without telescoping, you can guess that answer. So anyway, to play safe, I guess you should try to see all my review lecture, my review, and from there. But I have consciously avoided any things which I use only in review to be tested. Right? But my reviews are pretty good as a foundation to paint you a big picture to help you to study. So it should be no harm to go through my review. You can I play my own review myself at 1.5 speed because I speak too slowly. Somehow I feel I speak quite fast, but in the recording, I'm really slow. Maybe we are also used to YouTube and play in 1.5 times the speed. All right, so do look at the review and give you the big pictures and study carefully all the examples. You can see that I have make effort that for you to not just addressing question in the recitation itself, it's always helpful to create question yourself. This is how I created my question. All right, I created my question by teaching and knowing what are the difficulty and where are the possible place that some of you will get it correct and some of you may get it wrong, and therefore it become a good question. Okay, that's pretty much all about the midterm. Any more question? If not, then let's move on to the study. Midterm is just one process that we have to go through. The more important one is the content of the study. Okay? Just have fun for the next 2 weeks. All right. So I have prepared. So today it's the recitation number 5, working with sequences. You know, sequences include tuple list, dictionary, set. Set is it's a collection, not really a sequence. Anyway, so you have this equality to return true if the two objects are equivalent, means they are same value. But is actually the identical, mean they are the same object. So there's a difference between equality and is. And then membership in, it's to test for membership. And it says that there are 3 types of basic sequence, tuple, list, and range objects. All right, you see that range is an object. It's different from other iterator. Next week I will talk about it. We'll discuss list after midterm break. This meaning that the recitation, but list itself, it's a part of the test because it's until lecture 8. All right, which contain list also. The range type, it's immutable sequence of number and it's commonly used for looping a specific in this. The range has 3 numbers. The third number is optional. All right, if you have it, then you will be used. If not, then you will be assumed to be a step of if it's 1. Right? And then either this or this. In this case, there are 2 numbers or 1 number. If it is 1 number, then it starts from 0 and interval of 1. Okay. The range type is actually a constant space. All right, it's a small amount of memory. So instead of a tuple or a list, which is a linear space, if you have a linear amount of items in there, or you have n number of items in there. Okay, so let's quickly solve the problem here. So this is question number 1. So if you punch this into either, you will see the answer very quickly. Let me just get through this with you. Okay, let's take Aisha. Aisha,
Hi, Prof.
are you there?
Yes, Prof.
Okay, louder, please. Can you louder?
Okay.
Okay, good. All right, this one, let's go through. X equal to this, it's just there. X equal to this. A is this, so it's X is a tuple of two guy. The first guy is a tuple, the second guy is a tuple. Interestingly, this 1, 2, 1, 2, it's pointing to the same place. This is under Python 3.11. Okay, this is unusual to me, and I just saw this today, in a sense, when I'm preparing for this one. If this is Python 3.6, you see this is a tuple. This A is another tuple. This and this tuple are different. Okay, so for this question, somehow this is it make a difference. We'll see. B is this. B is X. So because X is this guy, so X is this guy. And 3, 4. And this 3, 4 and this 3, 4 are different because it's under Python 3.6. So let's check. X in A. X is this guy, that's X in A, it's the value. When we say in, right, in is true if X contained in the sequence type A. So let's see. True. Is that okay for you? Are you sure?
Yes.
Okay. So X is in A. X is in A. Okay. Then if I print X is A0, what is the return true if two objects are identical? What do you think this one will be?
X in A.
There's a difference between equality and is. The two objects must be identical, then you get true. Otherwise, you will get false. So is X identical to A0?
No.
Huh?
No.
No. Okay, so it's false. So let's try this for Python 11, 3.11. All right, X is this one, Python 3.11, and actually it is. So in this case, it's true. All right, so this is things that I mentioned before. If it is going to be different among different version or between different version, this shouldn't be something to test you. Okay, so X is in B. Oh, by the way, this tutorial it's more towards this recitation. It's more towards the Python 3.6. You see this question number 2 after we will encounter 1, 2, and this is 1, 2. By this example, these two are actually identical, so this will be true under 3.11. But we'll get to that. Print X in B, sure. What do you think?
True.
True. All right, this is obvious because X is embedded within B. X in C,
False.
X in C. What is in? In means return true if X is contained in the sequence type Y. So X is not inside C because X is embedded within another tuple, so it's not. So it's false. 2 plus 1.
2.
2. Why?
Because true is equal to 1. True is.
Okay. Yeah, and then?
So it can be added to 1 as
Okay.
well.
All right, so this is called promotion. This is a type promotion. All right, it happens that the Boolean type can be promoted to integer, and then therefore it can be added with plus. Okay, it can be added. So likewise for this guy, this is promoting the type. Promotion true is promoted to 1. Okay. So you will know that 1 plus false means what it is, huh? Okay. All right. And this is question number 1. Here. This is exactly this from here onward. Okay, let me try another guy. RJ.
Yes, bro.
Hi. So 1 equal to 1.
True.
True. And then 1 is 1.
False.
1 is false. All right, 1 is a primitive type. 1 is primitive type. This is true to me. True.
Oh,
Let me try 3.6. There's no difference. 1 is an object. It's a primitive type. A primitive type is going to be the same as the primitive type. There's only one primitive type. 1.
it points to the same thing.
Uh, In this case, well, you can say that, but it's just a number. It's not even shown here.
Okay.
Yeah. Okay, let's try. Oh, you cannot show because this is a condition.
Okay.
That means it cannot show anything. One. They are primitive. Basically, they are there. It's fetch into the CPU and check against each other. Okay, next one.
True.
True, because a double quote is the same as a single quote.
Yeah.
Next one.
False.
False, because this is an integer, this is a string.
False again.
False, of course. False equal to
True.
false. True.
True.
Okay, true equal to 0.
If false equals 0, true.
False equal to 0. True. Okay. True equal to 1.
True.
True. True equal to 6.
Uh, True.
Huh?
Is it true?
No. True is promoted to be 1.
Oh,
1 not equal to 6, I think. It's false.
okay.
Let's try 3.11. I don't think there should be any difference. False. Okay, next.
False.
False. Alright, it's obvious, right? This is 1 and a string of 2. This is 1 and 2. Next one.
True.
True.
It's
Okay.
the same
Isn't
thing.
these two the same?
Yeah.
How come?
Yeah, it's
Or
true.
maybe is it the same?
What to?
Oh, I meant to say maybe in. Let's try would it allow me to do this?
Then true.
This must be false, right? Is it
Is
true
it?
or false? False.
Oh,
In. What is in? X in Y. Alright. 1, 2 as a tuple is not contained inside here. This is a tuple with
Oh.
element 1 and 2. This guy is not in there.
okay.
Okay. But if you change it to be then it should be there. True. Okay.
Okay.
Next one.
1, 2, 3. True.
True. This one.
Order matters, so false.
False. Correct. So 1, 2, 3, 4, 5 is not the same as 1, 2, 3, 5, 4. Next. X is this, Y is this, Z is this. X is Y.
False.
This is X is 1, 2. Y is also
Why?
the same 1, 2.
Oh, then true.
True. I think this is the same as just now the case.
2 is
If you
2.
change this to 3.6, it will be different. Yeah. False. Because
Oh,
of 3.6.
then do we work with 3.6 or the 3.11? Like when
We
you
work
ask me.
with 3.11.
Okay.
But as I say, I will not want this kind of question pop up in the exam. Okay? I will try, this will be avoided. This kind of thing cannot be trusted. It's not the truth. And then, I don't know, 3.6 is like that, 3.11 is like that. Who knows? 3.15. Well, I don't know what happened there. Okay, so this kind of thing, you don't worry about it too much. You just know the difference, and we should avoid having them in the test. Again, tests can be contested upon returning to you after the marking. So you can always challenge us.
Okay, then
Okay,
this
next
one
one.
I take it as true.
This one, x equal to y. Of course, this has to be true, whichever version, because equivalence, this is check the content.
The east one, the previous one.
This one, previous one, 38.
Yeah, I
This
take it
one,
as, yeah.
you take it as true, yes, if it is 3.11. Okay,
Okay.
let's show only 3.11. Okay,
Okay, true.
x is z.
X is Z. Uh, yeah, true.
True, because they're identical, okay? X
Yeah,
is this object, z is the same object.
true also. 1, 2 in true.
Huh? What do you mean? This is a tuple.
Eh, 1, 2.
There's nothing here.
Oh, false. 2, false.
Huh?
2,
It,
no, true. This is not
yeah,
double.
this is trying to fool you. Is it
But
in
if
front of the
if got
question?
comma, then it's false, right?
Correct. Okay, so this is true.
Okay,
This one,
true, true, false. Okay,
okay, this is the value. X in A,
uh, true.
X in A. In 3.11 is true, yes. X
X
in
in
B,
B,
true.
true. Okay. 1, 2, 2, 3, false.
False. Okay, thank you.
Okay, thank
All
you,
right,
Prof.
now we need to do question number 2. Okay, for question number 2, this is actually talking about 3.6. So I need to, yeah, 3.6. All right, can you post your answers to the chat box and then I can see? Question 2. Iterative is also a recursive. Okay, iterative, most of you got it correct. Okay, so iterative, let me just copy it there. Did contain shortly. Let me just see the content first. And see the okay. For one, let's go one by one. So this one is this for item in tuple. If item is object, return true. Going through everything until the end. If you cannot find the return true, you return false. All right. So this is the code. What about the time? The time and space or what? Hmm? Anyone? Can you post? You want to? What's the time and space? Let's try. Ask me.
Shouldn't the time be the O of n?
Louder.
Won't it be the O of n,
O of n. Okay, why?
where n is the length of the tuple, because we're iterating through
Okay,
the tuple.
where n is the length of the tuple. What about space?
Space should be O of n as well.
O of n.
Sorry, O of 1
O
to
of
be a
1.
constant.
Huh? Oh, why O of 1?
Because there is no memory address that is required to hold the items.
Okay. I want to show you this. You say O of 1, right?
Yeah.
What happen if I need to do this? What is the length of this guy?
It's 2.
2, right?
Yeah.
Let's see the animation. Okay, tuple is this. It looks like this. Okay. The length is 2, correct?
Yeah.
Okay, now you go in.
Sorry?
Okay, this animation is telling me it doesn't create this guy in the item, it just refer to it. So the space is not, let's try 3.1. What happened to this? Item 1 is not, then next item. Okay. So when I take item out from the tuple, it actually it didn't make a copy of it. So in this case, the space is actually constant. So it just provided a pointer to, so there's no slicing or anything happening here. So the space is O1 as you wanted it. Okay, I just wanted to ascertain this. Okay, so this is not harming us. Right. All right, so the space is O1 as we wanted. Let's see the recursion. Let me see your recursion. I saw some recursion earlier on. Okay, here. All right, the recursion start with checking whether the length of the tuple is 0. If it is, then return false. Otherwise, you check whether the item is dead. Uh, if it is, then return true. Otherwise, you just recursively. So, okay. Here, the recursive version. All right. So, if tuple is empty, then nothing to check against the object, so it's false. Otherwise, you check the first item of the tuple is the same as the object you return true. Otherwise, if these both are not the cases, you have to slice it to get to the remaining of the tuple and the object. So what is the time and space? Let's see. Ayan, Ayan An.
Hi, Prof.
Hi. What do you think the time is?
O of n, where n is the length of the tuple.
O of n. Are you sure? These are all dangerous things, huh?
Oh,
This one,
sorry,
tuple slicing.
O of n square, because there is O(n) work at each level due to tuple
Uh-huh.
slicing.
O n square, where n is what?
Length of the tuple.
Of the tuple. What about space?
Is it also O(n) square?
Is it also O n square? Why?
Because at each recursion level, you're making a copy of the tuple.
Yes. All right. So I actually just now I give it away to you already. So actually you will try this. What's going to happen? Let's check this out. This one, right? Let's go in. Now we have this again. Hmm. Do you see what I'm doing?
Yes, Prof.
Yeah. What is your conclusion again?
I would say O of n, because it's just the length of the call stack.
Let me try one more. Okay. I'm afraid of this guy, actually. This whole thing, it can be very long, and it can be counted only for one. So for example, but because this guy only check item by item, I never make a copy. Oh, come on. Let's try. Yeah. Okay, so this guy never make a copy. So it's always pointing there. All right. Yeah, but these guys are stacked up in the length of the tuple. So the length was 5, then 4, 3, 2, 1. Okay, so this space is O n square, where n is the length of the tuple. Okay, that's correct. Okay, so we are done with the content. Next, we need to do the deep contents. Can you post in your chat box for me to see? Okay, I see Bruce. All right. This okay. If you don't check the type, you are not enough. Okay, Tian Tai, your code is not quite right, I think. All right, you have to, you miss out one testing, one checking of the type. Okay, the type you have to check, or is instance you can check. All right, so either you check the type or you check in. Wait, sorry, so it's contain recursive n or n square space. Yes, n square space. Yeah, it's n square space. Okay, so most of you are okay, except for one that miss out the checking of the type. Let me okay, so this is a recursive. What about the iterative? So most of you give me recursive. Anyone with the iterative? Oh yes, Chong Kai Yang. Oh, yours is so long. Okay, let me do one by one. So the recursive is here. If tuple is empty, then you return false, nothing to check already. Otherwise, you check the first item. Is it the same as the object you're looking at? If yes, then you return true. If no, then you check again. Now you check that it's the type is a tuple, and you check that the content is object is the deep content object with the first. If it is a tuple, right, you got no choice but to recurse into this function to check it, and you return true if this is true and this is true. Okay. Otherwise, you return the first guy is not already, is not this, it's not the type. Then you check this. All right. So here it's another version that it's a mistake. So this is the correct version. If this is this, then if you write it differently like this, if you write it like this, return this. Right? If this is a type, you return this, then this will be wrong. Why? Because if you do this branch will be executed and this branch will be missed. And in fact, the item could be at the back rather than in here. So this guy can return false still. So by doing this, this is wrong. If you do this, you have to change this to that will be hard to change, but you have to use an if statement, and this is true. Then you return true. Otherwise, this become inside here. You return this. So this become very complicated. So let me just change it back to the original one. All right, this is okay, but this is better to see. All right, so what is the time and space here? Anyone? Let's try. Xavier Quack. Hi, Xavier.
Yes, bro.
Hi. So what is the time and space for this case?
The time is n o(n) square, is it?
O(n) squared. And what is n?
N is the tuple length.
The tuple length? You mean this?
Yeah.
You mean the input tuple length?
Yeah.
And what about space?
Space is it o(n)?
O(n)?
No,
Okay,
o(n) square, o(n) square.
O(n) squared. Why?
Because creating a new tuple.
Okay, let's try this guy. What's the length here? 1, 2, 3, 4, 5, right? Let's see. Line 59. When this is the case, you see what I'm doing? So this time round, this is unlike the contents that all these guys are not involved. But now, all these guys are involved. It's creating this stack here. All right. So what I'm saying is that this n is not the input tuple length. Do you agree? Xavier,
Yes.
what should it be then?
Uh,
Actually, this is counting 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Something like that. You agree?
yeah. Agree.
Okay. So this is not correct. N is the total number of items in all the nesting of tuples. All right. So somehow these are very tricky, huh? at time it has the just now it run away with the content, it doesn't create anything. But here the stack it's leading up, so some of this stuff actually created the extra thing, even though it's only one, but it's still counting this thing. The safer is to make it into n square, where n is the total number in here as well. Okay, we are not very precise, but that should at least. So somebody say something. Is the worst case scenario for this input tuple is very deep nested or a very long tuple? It very deep can some of the deepness give you the extra stack item. The longness give you the slicing thing. So it looks like the longness is going to the longer it is, it's going to give you the ends contributing to the n square. But right, actually, yeah, that give me an idea about time. It's O of n square plus m of some kind of linear, where n is the length of the tuple, while m is the deepness, that kind of stuff. Okay. But in any case, if you sum both, you just make this into, all right, if you want to really precise, then this will be O of k square, where k is equal to n plus m. Okay, then you will be, this is play safe, Kiasu star. Okay. Can n for time complexity be rephrased as the number of leaves in the input tuple tree structure? Yeah. In the leaf tree structure. I'm just afraid that it's not necessarily a leaf. Okay, yeah. All right, I just want to point your attention to the possibility of this kind of strange thing. We never talk about it, but it can happen. Okay, and there will be a lot to ponder how these are actually affecting the time and space complexity as we see now. Okay, let me just go through the iterative. I think you have some iterative. Let me just cut and paste the iterative one. Yeah. All right. In this code, let's see what is the time and space first. What do you think the time and space? I have it here as time ON, and let's check it out. Let's check it out. Here. Okay, this is the long guy. Oh, it looks like each of these is still participating because of all this. So There's some depth to it. Okay, so I should correct myself. Is ON all right, this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, roughly there. Okay, so N is not just the length. That is not right. Okay, so I should run this with this example. Let me just comment out these two. All right, and I put here, this is wrong. If you return this guy, then it's wrong. All right. You have to, if this is the case, then you have to recursively in there to return true. Okay, let's try. A, B, C, D, and E. So this case 1, 2, X is there, so deep should be able to find it. This is true. 1, 2, B is this one, so it should be true. 1, 2, this is 2X, so this should be true. This is true. This is true. All should be true. Afterward, I'm going to show them false by changing the A. Okay, let's see. Okay, the last. Okay, they are all true. Okay, let's edit. I'll change this A to the next A, so it should be false. Okay, this one is still. Okay, I change to 1. Everyone should be false. All right, everyone is false. Okay. So the code is okay. At least proof by example, which is not supposed to be the case, but you have it. All right, I wanted to show you this. If I do this, this is going to be false for this case. So the first case is going to be false, even though the second case is true. Third case is true. Okay, let's see. All right, first case is false. So the code is wrong. This case X is indeed there, but it's false because I changed the code with this line, replacing these two lines. Okay, so much about this. So this is so wrong. This is correct. All right, this is question number 2. Question number 3. Are you okay for number 2 now? Okay, let's move on to number 3. Number 3 here. Okay, number 3, it's a higher order function, as you can see. Accumulate, it's doing accumulation. Just like many places, we define accumulate to be like this. 4 left to be like this and so on. You see many places in the midterm. Actually, some of this stuff are actually given already in Python, but we are defining it ourselves. And I'm going to give you a map for next week to try to create the map that is close to what the system gives. All right, so accumulate is to go through the sequence and with the initial value if the sequence is empty. Otherwise, you apply the function to the sequence with whatever this is. You have seen this thing before. That is accumulate. So if you study this carefully, actually this is the last one comes first. So if you have this equation, so the initial value is 1, okay, which is the y, the initial value is 1, okay, and the items here, if you trace it, of course you can trace it. Maybe let's trace it to take a look for one of them. All right, so you have this. So the sequence is non-empty, so you're going to the second one, and you're going to apply to sequence 0, which is the 1, and taking the value from here, which is the rest. As you do the recursion, you see that 1, it's stripped off, and then 2, 3, 4. Then 2 is stripped off, and you get 3, 4, and the 3, 4 strip off the 3, you get 4. Now 4 is the last guy. You are going to, of course, you haven't hit here. You strip off. All right, then you get empty. Now it's time to return. So you get the initial, which is a 1. Okay, a 1. And your value x is 4. The value is here, is 4. And this thing is 1. So that is what you get initially. And so what you want to do is the function is to do the function is to multiply the two numbers together. So 1 times 4 or 4 times 1. That is more accurately because x is in front and y is behind. So you get originally is empty and a 1. So you get 1 first. Then next round you get 1 and 4. X is a 4 and y is 1. You get the 4 here. Okay, you get the 4. All right, next the 4 times the 3, you get 3 times the 4, you get 12. And then the 12 times the 2, you get 24. 24 times 1, you get 24. Okay, you get 24. All right, so this is accumulating from the back. All right, so this last one comes first. And here you don't have a full write. The full write is in the lecture notes. Right, it's known as the full write becomes in the lecture. And so this accumulate and full write are the same. All right, so you are expect to see the same thing here. Then you can expect the full left to be in the other way. And so you have to take the last one, or this one shouldn't be the last one come first. It's the first one come first. The full left, so this is the first. So the first one come first. All right, so now it's from the front to the back. Of course, the meaning of this, you can always trace it to get this meaning. If you don't get that meaning, then every time you're given an example, you have to try it, and it's a hell. All right, like here. Okay, this is but once we understand the meaning, then we will be able to come up with this very quickly, the answer. All right, so you just have to, you're not supposed to remember any of this. Just The moment that they're given it, then you analyze it, you know which is which. Right, in this case, this one is the last one come first. 4, 3, 2, 1. And this one is last one come first also, because it's the same as accumulate. But this one is first one come first, from the front to the back. So the first one come first. So the y is initially 1, because it's the initial value. And x is 1, so x times 1 to get you 1. Right, so the x, this one is, let's trace this. Let's trace this guy, line 44. Oh, yes. There's another difference here. So now the x is the one that's coming from here. All right. X is the one coming from this, even though it's from the front to the back, and the 1 is assigned to the x, 2 is assigned to the x, and 2 times 3 is 6, 6 is assigned to the x. Oh, still the same. 1, 2, 3, 4 is here. Okay, let's see the 44. All right, so I don't remember any of this. I just have to be sober and try to figure it out on the spot. So let's see. Oh. Okay, so this is how you will see the 6, 4, and you get 24. Okay, so 4 left also give you 24. All right, so now these are things that you have to work out, and I have them for you. Instead of getting you to do it, let me just quickly get through them. So the 4 right, it's the same as accumulate. So it's from the back to the front. So from the back to the front, the first one is back is 3. So then the y is the 1. So you get 3 over 1 because you're talking about a divide operator. You get this. This is passed to the next one, which is 2. And the 2 has to be here. And the 3, 1. Then the last guy is a 1. So this is a 1. Divide by whatever is the previous one, which is 3, which is 1. Okay, so this is the answer. Let me call. All right, this should be the answer, and this answer is bracket 1.5. Okay, so let's 58, 1.5. Ah, 1.5. Okay. So what about this one? So this one is then the same. So but you have to start out with the 4 divided by 1 from the back, right? This 4 right is the same, and divide, so it's the same. Then you have to take this with the 3, and then you have to take this with the 2, And then you have to take this with the 1. All right, so I'm using the semantic of the code of full right to get this. Of course, if you don't do that, you have to trace it like hell in this case, because already by writing this is a hell. It's already so mind twisting. So what's this answer? This answer is 0.375. Let's check it out. This is line 63. This one. And 66. Three, 7, 5. Yeah, 0.375. Okay. So likewise, you can do it for the 4 left and 4 left with 3 numbers and 4 number. So let me just give it to you. The 4 left, it's starting from the front now. And so you have 1 over 1. And then you have to take it as with 2. And then you have to take it with the 3 from the front to the back. Again, you can trace this thing yourself to get this, or you can do it to get this with the semantic. So from 1, 2, 3 to 1, 2, 3, 4 is simply adding the 4 at the back. So, and that's it. This is 4 left. Now 4 right pair. Okay, now this is another headache. And the pair is to return 2 guy. Looks like this. And you're going to 4 right means you're coming from the back to the front. And 4 left means the front to the back. So how does it look like? So the first one is 4 right, it's from the back to the front. So you make a pair. So your X is the 3 and your initial value is this guy. So you get this. And then this guy, it's passed on to the next level, which is the 2. And this guy remains the same. And then this, it's going to pass to the 1. And the 1 is going to be there, and then the rest is the same. To avoid me having a headache, I can just copy this here and put a bracket. Okay, so this should be my answer. Let's see. This is the answer. And let's check. Line 72. Line 72. Yeah. Here. 72. This is the answer. Correct. Okay. So the other, it's again the same. This one 4 right is the same, but now it start with 1, 2, 3, 4. So 4 comes first. So let me just copy for you. So it looks like this. Step by step. All right, 4 first, then 3, then 2, then 1. On the other hand, this guy is 4 left. It's going to go from the beginning to the end. All right, so the first case is this guy with 1. So it's this with the 1. My cursor become this. And the next one is this whole thing. with the 2. All right, with the 2, so 2 with the bracket and another bracket in front. Then this whole thing with the 3. Right, in doing so, I actually understood the syntax or the semantic of this whole thing. So the same for the last guy. You get this. All right, so this take time to actually try it out yourself. Okay, that's number 3. Any question? You okay? Okay. All right, number 3, it's this. Then, give a property that Fn should satisfy to guarantee that 4 right accumulate and 4 left will produce the same values for any sequence. All right, so this property should be obvious to you now. Anyone? We talk about this often, right? What is it? Ethan, what do you think? Oh, associative. Okay,
Associative.
okay, associative.
Thank you.
Thank you. Associative. Associative. Okay. Yeah, so commutative, somebody asked. Do you need to be commutative? Huh? Anyone? What is commutative? Commutative means A plus B is the same as B plus A. Do we need that? I don't see it, but anyone? Chong Kai Yang. Why you talk about commutative?
Oh, I wanted to ask if, like, yeah,
Yeah,
can you say commutative? Because it's
yeah.
like for left and for right, it's like you can change the direction. Does that count?
If we talk about 4 right by itself and 4 left by itself, okay, I need to check. I know commutative means A plus B is equal to B plus A. Do you need that? Okay, I'll think about this, and if I have anything, I will post it up. Okay. Chong Kai Yang.
Yes.
Hello. Hi. Okay. Okay. As far as I know, it's associative. I can check some answers somewhere. Okay. Number 4. A queue is a data structure. So by now you know that a queue is a data structure that it's actually a derived data structure because it's not provided to you natively. That means it's not primitive. So you can implement queue. In this case, it's telling you to implement queue. Queue is a first in, first out. Okay, meaning that whoever comes first will be the first one to get out. Again, this is like in the real life. You have line up for food. You first come, first serve. All right, so you join the queue, and then earlier you get out of the queue earlier than those join after you. All right, so of course, again, here it's multiple representations, meaning that you can implement this thing with those kind of data structure that you want. It could be a list, it could be a tuple, but it doesn't make sense to be a set because you cannot arrange them in any order. Is no point in dictionary because there's no key value pair to talk about. So it's a choice between the list and tuple. So can I see your answer in the chat box? And then we'll see how. Anyone? All right, can you post something in the chat box? Nobody does this. Oh, okay. All right, empty queue is return empty set. So in this case, you're using a tuple. Can you do the rest? So if you are doing tuple, then you have a different kind of time complexity. All right, can I see the rest? Oh, okay, maybe I give it to you. This is too easy in some sense. Okay, oh, you give me this. Oh, James has something in different. A zero in the list. Okay. James, I'm not so sure what are the rest of the function. We have to see what the rest of your function. It it may be overdoing a little bit. We'll see. James, are you there?
Yes.
Okay, can you post your other functions? Uh, oh, empty queue is this, and queue is this Q1. DQ plus 1. Oh, can you explain a little bit?
Yeah, so the zero stores like the first index. So whenever
Oh,
you access
okay.
like you DQ, then you add the index by 1. Yeah, so
Oh,
the length of the queue will get longer and longer.
DQ you add by 1. You subtract by 1 or you add by 1?
The queue is just append at the back.
Okay. Oh, I see what you mean. So you are having double pointer.
Yeah, 2 pointers.
Yeah, okay. So you can achieve O1 all the time. Okay, that's quite good. Um, so your queue never get destroyed. It just got moved forward all the time. Yeah, that's fine. Yes, you are not overdoing. You are making it into a more efficient manner. Whereas if I use the normal one, which I have to pay the price of taking item out from the queue in ON time, but you don't. Okay, so you are smarter. Okay, here it's what I have, which are not as good as James. Um, let's see, but I'm using list also. All right, what I meant is that James DQ is actually constant O1, but my DQ is ON because I remove one item. All right, so you can use James one, which is more efficient. So that testified to the fact that, in fact, we have multiple representations, and if you are smart enough, then you will be able to come up with something to suit your purpose. For example, in this case, ON could be very dangerous because the queue could be very long. And if you take item out from the queue and you pay for this, this is no good. On the other hand, the James version will need to be, you may have to clear the queue, right? The queue cannot be built up all the time, or unless you know that this is an application with the queue never exceed a certain number, or the application will be killed after some time, then you can do this. Otherwise, this is like a memory leak kind of thing that the front part is useless, but yet you keep them. Or you may have to, in James' case, he may have to write another routine to clear out the memory, like doubling kind of stuff, to help to achieve the constant time to DQ at the same time save in the storage. Okay, so there's quite a lot of room for expansion in this case. Thank you, James. James. All right. So this is no good. So you can consult the version from James and see they are a lot of things that you can play with. All right. So this is a version with list and not a good list. The tuple even worse, I guess. But on the other hand, I don't like this question that it has to return a queue, because by right, when you do the queue, right, the queue should still be the same. You don't have to return a queue. You can just pop up and the queue remains. So this is not so good. Anyway, it again testified to the fact that you can have a lot of ways of doing things, and maybe this version is good enough for your application. So it still work. All right, so you could see the answer. We do get 565, which is the answer. All right, so this is question number 4. Yeah, okay, give me a check. Question number 5, another headache. Okay. All right, question number 5. Here again, you are told with tuple 1, 2, 3, 4, 5, 6, 7, you're supposed to use map, filter, accumulate, or lambda to do your thing. So let's see. All right, A, this should be an easy one. 1, 4, 9, 16, 25, 36, 49. Coming from 1, 2, 3, 4, 5, 6, 7. What is it? It looks like you are just simply mapping. All right, there are 5 things that I told you: mapping, filtering, accumulating, searching, and sorting. All right, searching and sorting are not here for today, but they are accomplished. They are actually partners to these 3 things. All right, so let's see what you have for A. This should be easy. A should be easy. Anyone? Okay. Okay. Yeah, it's simply a map. So, all right. So if you do just the map, there it's another thing to note. If you do just this map, or like number 10, line number 10. Yeah. Okay, I see line number 10. You get an object, okay? You don't get a value. This is what all these objects. This guy is actually an iterator. Map, the system map, it's giving you an iterator. So if you don't want the iterator, then you need to make it into a tuple. So there will be a tuple here. Okay? Or you write your own map, but this map is a system map. All right, you get 1 point, you get this. Okay, so I see that one of you already, Isaac Lama, Seva, Garnish already used the tuple. Okay, the tuple is needed here. B, let's see B. In the exam, if we want to refer to the non-system map, can we just say in the working that we are not using Python's map? Sure. Right, I think this will apply generally. Whenever you have doubt about our questions, or you are using something not required from the not explicitly stated in the paper, you can make all your assumptions, and on the safe side, you protect yourself by putting the assumption in the script that you submitted. Okay, that's correct. Just like your working, if you show some working, though I claim that I will not give you method marks, but sometimes out of sympathy, who knows? Or if you see that we can argue you have just made a typo or something, then we will give it to you with a small deduction. Okay, B. Let's see B. What is B trying to do? B is 1357. So this is 1357. It basically is filtering out things. All right, so I see what you have. Okay. So B is filtering. This is filtering. And because this is again a system, you must put a tuple there. Let's try. All right, 135. If you don't do the tuple, let's see what happens. Pi is an object. Okay. And also be careful when this is an object. This is an iterator, then you will use it up, you will be gone. Okay, C. What about C? C is this. Oh, this looks like a pair. All right, so one pair with one, two pair with two, three pair with three. And the whole thing is again a tuple. So we need to use pair. So the pair have to come back. Where's the pair? Oh, the pair, you don't need it. You just simply use directly yourself, the pair. Okay, fine. So let me just put it there. See. All right, the pair. We make the pair ourselves. Basically, it's a map of every element into this guy, and X is this guy. This X and this X are different X, huh? Right, this is intentional. This can be I and I. Without changing this, it has to be X. X is this one. Okay, that is C. What about D? Oh, D. D is, you are not using accumulate. Okay, accumulate. All right, let me see my accumulate. D. Accumulate is 4 right? Accumulate is 4 right. Okay. All right. Hey, this Wang Yuxiang. You cannot do this if y equal to 6 or y equal to 4. This become like cheating. You cannot. In this case, I think it's become not general. Also, the Gangaharan. I think yours also. You cannot explicitly put the number there 2, 4, 6 like that. Okay, you have to, because in some sense it should work still if I change my X, I'll extend it to 8, 9 or whatever. All right. But if you can do this, why don't you just print out this directly, or you just print out this directly? So it doesn't serve the purpose. You shouldn't be meddling with them. You should do checking with. These are even number, so you have to keep the even number in some sense. Okay, what I have here is D is 4. I'm using 4 left. I'm not using accumulate. All right, maybe this is just giving you, you are encouraged to provide multiple solutions. So let me just give you the 4 left. At least my 4 left. I needed to use a if statement. Oh, what is my XX? My XX is actually a tuple. I could just substitute it here. Okay, it looks like this. Oh, it doesn't give me bigger. Okay, to make it more readable, then I should remove these two. I put XX, and my XX is equal to this. Basically, my even number. Okay, this is my full left. Oh, I cannot run already because I needed to put my full left up there. So I need my full left. Okay. Let's see the E. E is looks like it's also like full left, right? The two first, then four, and so on. Can I see your E? All right, so now you should learn that you can use if statement to play around with whether you want or you don't want. Okay, so this case it's E is this one. All right, so it's I say this is tricky because if the first one you don't want it, you just remove it, and otherwise you have it. Again, my XX refer to this guy, my even number. Okay, that's my E. F is kind of easier because you're supposed to get the largest number among them and also get the minimum number. Okay, let's see what you have. F. Okay. All right. So it looks like this. All right. You accumulate using the max function, which you can write yourself also. And initial value is the first guy you use, and then compare with the rest. That is your maximum. All right. You accumulate, you check one after another. This guy is the initial maximum, and you check. Oh, it's from the back. So if you run this, you can see which one comes first. So accumulate comes from the back. So, but you're using the first item to be the maximum, and then you go from the back and compare. So 1 compare with 7, 1, and then 7 win. So 7 compare with 6, 7 still there. 7 compare with 5, and then 7 still there, and so on. Okay, that is F. The G is the same, right? Minimum. Just change this equality, this thing, and change this to minimum. Okay, so this. Then H, the maximum square even element of X, 36. Oh, so you are only taking the even number and square it. So 6 is the largest that you square. So it's simply 2 steps. This is so-called the signal processing way, right? So you pipe this list and filter out those odd number. Then for those even number, you keep it and you calculate the maximum, or you can filter it out at the same time. You or you can square it and then filter it out. Also can. All right. So there are many ways. So let's see this one. H. is this. I do accumulate also. I do the x-axis is already filtered. My x-axis is those even number. Those even number, I calculate their square. Then I calculate the square of all the even number. And this, because it's a system map, I make it into a tuple. Why? Because my accumulate is my own accumulate. All right, in the previous question, or previous question number 3. So I have to work with actual number, not object. If I take away this, it becomes an object, I cannot work. And the maximum started with 0 until among them, which one is largest? 36 is largest. And last one, the sum of the square of each number in X. Oh, you have to square, and sum them up. So basically, you can square first and then add them up using accumulate. So you square first, make it into a tuple because it's a system map, and then you add them up one after another, and that's it. Okay. All right, we exceeded the time. You okay? Give me a check if you're okay. Okay. This is a long one. I owe you one thing about associativity and all right. Any question? If not, then we call it a day. Okay. Anything? If you have a question, you post it in the chat box. Else, we call it a day. All right, so you should remember that lambda has this kind of format, if else, no colon, nothing. And you can use it to filter away. You can use it to exclude. In this case, is a trick that you exclude it from using A, and the rest you use A. All right, things like this. Okay, any question? If no, then good night. Bye-bye. Okay, bye-bye.